Okay, good afternoon and welcome to the Pipeline Industries Guild webinar. Today we are presenting the superior solutions of marine HDPE pipes for Asian power plants. This has been organized by the Guild's Intake, Outfalls and Landfalls Technical Panel. My name is Martin Berry. I work for Royal Haskell DHV and I'm the chair of the technical panel. And I would like to introduce today's presenter, who is Ilya Radilic, who works for Pipelife and has been with Pipelife for about 13 years, involved with the manufacture and design and installation of long string polyethylene pipes for marine pipelines. So welcome Ilya, and I will hand over to him to do the presentation, and we will go through the questions at the end of the presentation. Thank you.
Thank you very much, Martin. First, I would like to say a big thank you to you and the Pipeline Industries Guild for this opportunity to present some of the projects that Pipelife is working on. Then I would like to thank all the participants and interested parties that are separating a little bit of time to see this presentation. And it has a lot of very nice information as well as visuals, so I really hope that you will enjoy it. So the topic of today, as Martin has said, are the superior solutions for marine HDPE pipes for Asian power plants, and superior solutions as we as Pipelife consider them. Through this presentation, I hope you will understand why we call them superior and what were the actual causes in these two projects that led to the selection of our pipes as the best solution. So the key takeaways that I hope that you will learn from this presentation are the superior marine solutions and why we consider as such. In principle, it is because other pipes of other materials have failed, be it of concrete, GRP or steel, or were found unsuitable for the application. Then reliable marine infrastructure in weak soils. This is the problem that was tackled in these two projects with silty beds up to 30 meters. So very weak soils. Why Pipelife was selected? And Pipelife was selected because of our tradition, experience, and reliability. So we have been doing this business for over 25 years, and we have over 140 major projects delivered. We have delivered the pipes in the very long range, from Norway all the way to Malaysia, and that is over 28,000 kilometers, almost 28,000 kilometers by sea. The pipes have a very fast submersion, 300 to 500 meters per hour. So once the pipes are in the position, you can sink them very, very fast, which limits the exposure and the risk involved with the marine pipelines. The pipes are also earthquake resistant, which was one of the critical requirements for the power plant in operation. The pipes are also come with low risk. And why do we say so? Because there are very few welds on these pipes. It has a very robust assembly, and the limited exposure during the installation is crucial to minimize the risk of the entire marine pipeline installation. The pipes are also of high quality, and we base this statement on our production. So we are seamlessly producing the pipe into the sea without any welds. The only welds which are present on the pipes are at the very ends of the pipe, just to enable the transportation and later on connection at the construction site. In addition, polyethylene has no corrosion at all in the sea. The structure of the presentation is as follows. So first, we will go through a very small introduction. Then we will talk a little bit about these projects more in detail, who are the stakeholders and where these projects are located. Then we will again talk about why long length, large diameter pipes are selected by these stakeholders. And you can see these pipes in production on the picture on the right. Then we will briefly talk about design, production, towing, and installation. And since one of the projects is in the construction stage and the other project is already in the operation stage, we can compare these two projects, and we will have several different pictures showcasing their various statuses. Another big point from Pipelife is engineering support. So all these projects required very specific HDPE-related engineering, which Pipelife has provided to support the client. And in the end, we will wrap it all up with a small conclusion, and I hope you will agree with the points presented in this presentation and wrapped up in the end. So as said, a small introduction. Pipelife has been selected as a marine pipe solutions provider for critical national power infrastructure in Asia. This is very important to note that these projects in Asia will be supplying thousands of homes and businesses, and they need to be reliable. And our pipes and our experience show that we can look at decades and even maybe centuries of use of HDPE pipes without degradation. This presentation will showcase two projects. One is in Bangladesh and one is in Malaysia. We will go into the details on the next slide. Each project also had different challenges to overcome, and which were the main reasons why Pipelife has been chosen, why solid wall pipe has been chosen, and then we will go more into the details of those. So the first project I will describe is the Tanjung Kidurong power plant, which is located in Malaysia on the island of Sarawak, and it is already in operation. It was a joint venture between Power China General Electric, and this project used our pipes as intake pipelines. The second project is Matarbari power plant. It is located in Bangladesh, and it is again a joint venture of powerful Japanese companies, as well as a powerful and big contractor, which is POSCO Engineering from Korea. This project is still in construction. The pipes have been delivered and are on site, and are to be installed preferably next year. That would be 2022. So why long length, large diameter pipes were chosen? So let's start with the Malaysian project, where these pipes are used as intake pipelines. So the previous pipelines, which were made out of steel and GRP, have actually failed. They had issues with the sinking, dislocation, or cracking due to the strain in these weak soils. We are talking about extremely weak soil, up to 30 meters and even more of silt soil. That's extremely difficult to reinforce or change that soil. So the client and the contractor had to find a better solution, and it was found in our pipelines. Also, the added benefit was that these pipes could be backfilled with excavated materials. So solid wall polyethylene pipes can be backfilled with the excavated material, which saves on time and cost, of course. There is also a very low risk of sinking or floating when you're using solid wall pipes. And this was one of the main challenges that we have addressed in the engineering. If you use more traditional materials, such as steel or concrete, then you have a very high risk of these pipes sinking into the soil. And you need to take care of that, which is, again, increasingly difficult to do if you have a very, very weak soil for a lot of meters. Another issue, which again arises from the weak soil, was that quick installation was needed, and that was in order to avoid trench maintenance. Because when you dig the trench and you have the wave action going on, the trench will slowly fill up, especially in this kind of weak soil where the slope needs to be very, very mild. So once the trench was done, it was imperative that the pipes were installed as fast as possible. With our solution, that is possible, because once the pipe is in position, you can install it in a matter of hours. We will come to that a little bit later on when we touch on the installation. And in the end, the reliability of long intake pipelines in the seawater is something that is very important, because HDPE will not corrode. It is one of the biggest issues that faces all other materials. In addition to that, it has very, very few connection points. And if you have the pipes in long length, you don't even have the welds. So there are very, very few weak points in such an assembly. For the Bangladesh project, the pipes will be used as outfall pipelines. As I mentioned, this project is still in construction. So why did the stakeholders in that project choose LLLD from Pipelife? Because, again, we are talking about relatively weak soil. The pipes are also in a tidal zone. That means that they will be partially submerged, and it is relatively difficult to install the pipes in such an area. Also, one of the main concerns from the end client was the earthquake. So it was important to have a solution which will be earthquake resistant, which we have through our documentation and the case studies from different projects, proven to the client that by using solid wall HDPE pipes, the risk of earthquake and any damages that could occur due to the earthquake are very, very, very low. In addition to that, there was a requirement that the pipes need to withstand a typhoon, and that means very large waves in small depths. So we had to design a special ballast blocks to withstand such an event. In addition, the project is in a very, very remote location, and it is very difficult to reach by land. Also, there is limited space on site. All that combined means that any kind of land delivery of short length pipes was almost impossible, because you don't have the space to store it, you don't have the space to weld it. So our solution with the pipes delivered by sea was perfect for the client, because they could do all the operations at the sea and install them directly on the sea where they should be installed anyhow. In addition to that, quick installation was needed to avoid the complex installation under the tidal movement. So again, because we can install the pipes in a matter of hours, then you are avoiding all this risk and complexity that comes with the tidal movements in that area. And last but not the least, the backfill with excavated material is something that is extremely important in relation to the logistics on site, as well as cost benefit. Now let's touch a little bit about the design that was done in this project. So Pipelife has provided extensive engineering and support, which is related to the specifics in relation to the pipes, their assembly, and installation and stability. So there were several problems that had to be tackled in this project. So we had to find a solution to have the pipes neutrally buoyant in weak soils during the liquefaction event. We had to design the ballast blocks. We have provided also the pipe on-bottom stability and pipe submersion analysis. We have provided supervision on site, as well as small minor parts of the assembly, such as compensators design, cathodic protection design, or even the band restrictor design. The pictures of some of these are shown on the right-hand side. The biggest challenge in Malaysian project was how to achieve the neutral buoyancy in weak soils during the earthquake events or during the storm events, where we could have liquefaction of the soil. Because again, very weak soil conditions up to 30 meters, such an event was had a high probability of happening. So the solution that Pipelife has engineered and proposed, and which was in the end adopted, was to have the right size of the ballast block at the right spacings, so that the pipe would be neutrally buoyant even after backfilling and in the case of liquefaction. What that in practice means that if we have an earthquake and the soil liquefies, the pipe would not either sink nor it would rise up. It would just remain stable where it is. So with some smart calculation and smart engineering, that was a solution that Pipelife has provided and the client has adopted and the contractor has installed as such. It is worth noting that other pipe materials have actually failed or were found unsuitable in these conditions. For the Bangladesh project, again, Pipelife has provided extensive engineering and support. There were a lot of soil movements and settlements to be expected. So that had to be settled and had to be calculated for, and that there are no risks involved in the movements and settlements of such soil. Also, Pipelife has provided concrete ballast block design, which has a relatively specific, because it had to be longer because of the limited space where the pipe could be located. So there was very, very limited space, and you had to put 6 pipes parallel to each other. So the ballast blocks had to be very narrow and very, very long for the purpose. And Pipelife has designed 2 such blocks, and one was for the offshore where we had that typhoon requirement, and the other was for the more or less protected inshore area. In addition to that, compensators, cathodic protection design was done as well to have the complete assembly ready. Pipelife has also provided on-bottom stability and submersion analysis for these pipelines. So all in all, an engineering package which is targeting specifically the very narrow field of solid wall HDPE marine pipelines. The most challenging part in Bangladesh project was actually achieving the sufficient pipe support under the soil load, because the chosen pipe was SDR30, 2.3 meter in diameter, and this pipe has actually relatively low load capacity, which is not usually a problem on land, because you can use the soil and you can compress the soil around it to stiffen it. But when we're talking about marine installations, you usually don't have that opportunity. So we had to find a way to stiffen the pipe where it is needed. So we have designed it in such a way that we have ballast blocks which have different spacings along the pipeline. And these spacings are reduced when the pipe needs to take a lot of load. So the load will be transferred through the blocks to the soil. And such locations are, for example, in the breakwater section or in the manhole section where there needs to be an access road on top. And we are talking maybe about 5-6 meters of heavy soil load on top of the pipes. So the smart solution was to play with the assembly of the pipeline to withstand all these loads. Now let's talk a little bit about production and some interesting facts. So for the Malaysian project, the pipe which was produced was 2.5 meters in diameter, outer diameter, and in total, a little bit over 3 kilometers was needed. These pipes were produced in lengths of 555 meters, and there were 6 of those. In the end, these pipes were installed as 3+3. So we are talking about 3 parallel intake pipelines on the construction site. As you can see on the picture, we have a seamless production without welds directly into the sea. And as the project requires, we then cut those pipes in the lengths that are needed. So in this project, it was 555 meters, and we can produce up to 620 meters. So we can just produce custom lengths as needed. For the Bangladesh project, we had more kilometers, almost 7 kilometers in total. We are talking about 2.3 meter pipe, SDR30, and 12 pipes in total. The length of the pipe ranges from around 500 meters for 6 pieces and 620 meters for 6 pieces. For Bangladesh project, we are talking about 6 parallel outfall pipelines. So there will be 6 parallel pipelines delivering the water out from the power plant to the sea. Again, we are talking about seamless production without welds directly into the sea. And as you can see, the pipes will be cut, actually were cut in the custom lengths as the project required. Our picture on the right shows our factory and these pipes in the bay ready to be prepared for the long transport. So now let's talk a little bit about the towing. And I'm very excited about this one because it is still the world's record in transporting the solid wall pipes, actually towing them to the location. The entire trip lasted over 6 months. We have passed almost 28,000 kilometers, and it is the first tow to Asia from our plant. And I would say it is the first tow to Asia ever of any solid wall pipe in long length. The pipes have arrived without incident on the destination. On the right, you can see the picture of the route that we have taken, and it was around South Africa all the way to Malaysia. A fantastic trip which lasted over 6 months, and we were monitoring it daily, how it developed. For the Bangladesh project, we have done another milestone. So we have decided to pass through the Suez. There were several technical requirements that prevented us for doing it before, but now we have managed to arrange it. And we have considerably shortened the time needed to deliver the pipes, as well as the distance. So we are now talking about 17,000 kilometers, and the pipes have also arrived without incident on the destination. Because Suez was such a major challenge for us, I have decided to show you a little bit more details about it and what kind of requirements we had on it. So first, you can see that there's a lot of risk involved in such an operation, and Suez operation was a special risk that needed to be handled and taken care of together with our insurance company and the marine warranty surveyors and all the other companies which were involved in ensuring that we have a smooth sailing. So 6 months of preparation was needed, and I'll just briefly go through all these points. First was overall risk management of the entire project and specifically the Suez. There is also minimum speed transition challenge which we had to overcome. So basically in the Suez, you need to move at a certain speed. We were below that speed. That would mean that we would be blocking or slowing down the entire transit. So that was an additional requirement for the entire channel passage and how to tackle it. There was special requirements from the survey insurance aspect by the marine warranty surveyors that needed to be addressed. And then we had to discuss how are we going to move in a convoy through the Suez. Is it before convoy, after convoy, in the middle of the convoy? So there were various options that were discussed. We were also looking at the waiting time outside of Suez. So if we cannot join the convoy for whatever reason, do we need to wait? How long do we wait? How do we rotate the pipes in the sea? And how are we going to deal with all that? On top of that, we needed to have Suez agents on board and the coordination for this entire trip. On top of everything, after the Suez Channel, we had to have armed guards on board, as well as hardening of the tug. This is the concept that we had to introduce in this trip. And hardening of the tug means that basically the tug had several locations on it, specifically reinforced against forced entry, etc. So it was very interesting to see how the companies handled that and how we had to also think of all the other options, not just the technical aspects of the travel, but also the other unforeseen issues that could arise. In the end, just to make a small drone filming, we had to hire in a special company. There is only one company allowed to do so due to the military installations which are along the channel. So you can already see that there's a lot of challenges that had to be overcome just for that small pass there. But in the end, we have made it, and we have made it with a big success. So we have actually made 2 world records there. The first one is the longest marine unit that has passed through the Suez. So the previous longest unit was 450-meter long ship, and now we have passed with our pipes, plus the tugboat, plus the wires, and the length was around 700 meters. So it needed a very special attention from the canal authorities, which we got in the end. It is also the first time that towed HDPE pipes have passed through the Suez. We have received a very special VIP treatment from the chairman of the Suez Canal Authority, Admiral Osama Mouanin Rabi, who was on board the tug. And you can see on the picture on the right that he is overseeing the whole operation fully from very close up. There were no incident or issues. And remember, just recently, there was this Evergrande incident in the canal. So you can imagine what kind of scrutiny we had to do to avoid such a potential incident. Also, you can see on the pictures that our VIP treatment is not just a joke, but a reality, because you can see that the whole canal was cleared of traffic. So there is no ships in front, no ships in the back. So the canal authority had to arrange our trip in such a way that we had a smooth sailing with our relatively slow speed through the canal to avoid any kind of incidents. So thank you very much to them for treating us in such a way and enabling this passage to be a true success. And now let's talk a little bit about installation. So back to the project in Malaysia, where the pipes have actually been installed. So I will show you a little bit more about how that process went. The Bangladesh project, as I said, is still in construction. So there are no installation pictures yet. So for the pipes to be installed, they first need to be prepared for the installation, and they need to be stored somewhere. So in Malaysia, they have stored them in a river, where they have put the ballast blocks on and connected the pipes into longer strings. So remember, we had 555-meter long pipes, which were connected one by one into one long string, which is around 1 kilometer long. Also, to protect the pipes, there was this bend restrictor, which Pipeline has designed to reinforce this connection area. One interesting detail, the assembly of the ballast blocks had to be done in a river, and the river is actually full of crocodiles. So you can just imagine what kind of special health and safety regulations there had to be in place for such an operation. Again, without incident, everything was done perfectly. Once the pipes were connected, they had to be transported outside of the river to the project site where they were to be installed. You can see on the picture how the pipes were connected into 1 kilometer long string, supported by the tugboats, and taken outside of the river into the open sea. Still with the ballast blocks on, you can see how easily the pipe is bent, and this flexibility is the key of using polyethylene in the seawater, because it will adjust to all soil movements, wave movements, etc., much more easily than the other rigid pipes. Here is a nice picture of the pipes being transported on the open sea once it has exited the river. It was a relatively short distance of around 40 kilometers. There were many supporting vessels on the sides, observing the towing and following the pipes to the installation location. Once the pipe string has arrived, it was positioned above the excavated trench. And once it was aligned, the submersion of the pipe could start. It is at this point that the actual best benefit of HDPE in long length can be seen, because the sinking or submersion of 1.1 kilometer long string lasted only 3 hours. So you need a very small weather window to completely sink the pipes down. Everything was done in 1 day. So from the transport of the river to the installation was done in 1 day. So all the other operations can be done in a relatively safe environment. So the storage and ballasting, etc., can be done in a protected area. And you only need one day of good weather to install the pipes. Then the backfill can be done by dedicated vessels. It went fast and smooth. It was backfilled with excavated material, which was lying on the sides of the trench, and there was no need for bedding. All this was done during the engineering phase to ensure that we can actually use the excavated material, and that we can that we don't need the bedding, and we can then propose the assembly that will fit these requirements. So just to wrap it up, in regards to the engineering support, it is for both projects important to have this special know-how that Pipelife has, because we are experts in this, because we have been doing this for 25 years, and we know polyethylene, we know marine pipelines, and we know how to assemble them. So we have this very specialized engineering that we provide to the EPC contractor. That also creates a high competence and experience, which results in a trust between the stakeholders in the project. And it is important to note that Pipelife is a solutions provider. So we are not just a pipe supplier, we are a solutions provider, and we can deliver the assembly best practice, optimal lengths and connections, diffusers and intakes and manholes best practice. We can provide pipe stability analysis, pipe submersion analysis, and on-site supervision, support, and guidance. All this is a nice package that, to people who are not familiar with HDPE, we can help to overcome the fear and to have a trust and trust in Pipelife as a supplier, and trust in HDPE as a solution for marine pipelines. And now to try to wrap it up in a conclusion. So despite the challenges in regards to distance, and I'm talking here about Norway and Asia, the contractors and asset owners have selected long-length, large diameter pipes for their critical energy infrastructure. It is important to know that these pipes have traveled a long way to ensure their critical energy infrastructure. This demonstrates a high degree of confidence in Pipelife for the projects to come in the region. And in the end, just let's talk about the benefits, and the benefits can be divided into two major groups. One is the benefits of using our pipes for the asset owner, and the benefits of using our pipes for the contractor. So the benefits for the asset owner is that they are dealing with a reliable and proven solution, and we base this opinion on 140 and plus projects. It is a long-lasting solution, so the polyethylene can last over 100 years. There are only 2 welds per 620 meters, which results in a very safe and robust pipeline, because there are no weak points, and if there are, they are very, very far away. The HDPE and solid wall is earthquake resistant, so if there is an earthquake, the pipe would just be potentially displaced, but it would not break or have any kind of long-term damages. And this is supported by the reports from Japan earthquakes or New Zealand earthquakes, where their pipe networks were analyzed after the earthquakes. And the result was that solid wall polyethylene was the best material for it. And also the HDPE is resistant to long-term soil movements. So if there is any soil movement in these weak soils, the HDPE pipe will easily resist them. So the benefits for the contractor is the quick installation. As you have seen, once the pipe is in position, you need 1 day of good weather to install the pipes, and then everything else is just dredging or backfilling. So the pipe-related work can be just 1 day. Welding on site is not needed, so you don't need the costly logistics of the welding machine, welders, on-site ramp, and etc., and all the other things that come with the short-length solutions. Ballasting can be done on sea in protected areas, so you can do it either in port or in the river as showcased in this project. There is no storage or logistics on land, so you can do everything on the sea, which prevents damages and other things that can occur on the land. And in the end, there are no backfill requirements, so we can design our pipeline in such a way that you can utilize the stiffening effect from the ballast blocks to not have special backfill requirements. And in that regard, you can have a very flexible installation on site. And that would be all. Thank you very much for your attention, and I would be happy to answer any more questions.
Thank you, Ilya. That was a very interesting and comprehensive presentation. We have had quite a lot of questions that have come through, so we will try and go through those individually. There are a few that I think there's a little bit of overlap, so with a few of the questions, but okay. So the question is, why reference to cathodic protection in HDPE?
Because when you are connecting the pipes, you usually have a backing ring and you have a flange connection, and that backing ring is made out of steel. So you need to have a certain protection of the steel parts in the assembly. So even though the entire pipeline is in polyethylene, the connection points utilize certain steel elements. These steel elements need to withstand and need to have a cathodic protection for the longevity, which is predicted for the pipelines, which is usually 50 years. So we can design such a cathodic protection that will last for 50 years or whatever is required passively. So you don't need to interact with it. You don't need to provide electricity, etc. It will just be mounted, and it will be sacrificial, and it will be there.
Okay, second question. How did you manage adverse climate during towing?
Sorry, could you repeat?
How did you manage adverse climate weather during the tow? So
we know from experience again that the pipes can withstand the waves even up to 10 or 12 meters. So we know that the pipes can handle such issues without a problem. The issue that might arise is for the tug itself, because the tug needs to seek shelter. So how we utilize in these long trips that we have ensured that the pipes and the boat will have certain places where they would stay, inspect the towing gear, etc., and that we will have certain refugee points in case of bad weather. In some cases, we had to avoid the incoming bad weather, so the ship had adjusted the routes. So we have very active focus on the weather forecasting during the entire trip.
Okay, what was the maximum water depth for the installation, as SDR rating of 30 seems low for deeper water?
SDR 30 is a little bit on the thin side, but for this particular project, we are talking about a very shallow water. We are talking about 5 meters in the shallow part and up to 8 meters in the deepest part. So from the installation perspective, SDR 30 can handle it without problem. The problem came because we had a lot of load on the pipe on certain areas. We had to be handled with the ballast blocks instead of the wall thickness.
Why did you not tow through the Suez Canal for the Malaysian project?
Because at that time, Suez Canal was still experiencing certain expansions, etc., and it was difficult to negotiate with the Suez Canal Authority about the passage of our specific pipes. When Suez Canal Authority was ready to discuss in detail our transport, and we actually had the upcoming need, then we have managed to reach the conclusion on it.
Why is towage preferred instead of site assembly?
Because the first thing I would like to point out is the quality. So if you're doing any kind of welding of the pipe, you're introducing a potentially weak point every 10, 12, 18 meter, whatever is the short length that you are welding. Since this welding needs to be done on site, it is very difficult to have consistent control and consistent quality of the pipe. Since we are talking about very large pipes and relatively thin wall pipes, SDR26 and SDR30, any kind of mistake in the welding can be fatal. So if you're installing 1 kilometer of pipe and it is welded, then you have a weak point every 10 meters. That's a lot of potential risk points. And if one of those welds would not fail, but just start to leak during the installation, you will have uncontrolled installation of the pipeline, which would be extremely costly and difficult to remedy. So the quality would be the number one. The second one is you need to have logistics on site. You need to have the welders, the welding machine. You need to have a power supply which is uninterruptible, because that is related to the quality of the weld. You need to have potentially a place where you can have all these pipes stored. You need to have possibly a ramp to launch these pipes. So there's a lot of logistics that you need to have on land for doing the welding in the short lengths. And in the end, when we deliver in long lengths, it is high quality, all is done in the factory, you just connect them on the site, and the contractor can focus just on connecting and ballasting instead of the whole process of actually making the pipe to the lengths that is desired.
How much time did you save by going through the Suez Canal versus going around Africa?
It depends actually on the project where it is located in the Asian side, because it's not the same to Bangladesh and Malaysia, because it has different traveling routes. But in principle, it depends very much on the setup for the Suez. Do we have a waiting time in front of the Suez or not? As we have seen that the waiting time was very, very limited in our case for Bangladesh, which was very positive experience for us. We were anticipating possibly weeks of waiting, but in the end, we have waited maybe 1 day. So we have saved overall, I believe, around two months by going through the Suez.
How are the ballast blocks fixed in the river?
So there are various ways you can fix the ballast blocks. The one method which was chosen by the contractor was a simple L structure, where you have the like L-shaped steel structure, where you have the ballast block here and there, and then you just leave the upper part, move it over the pipe, and lower it. Then it is bolted together.
How are the pipes connected to each other on site?
So the pipes are connected like a normal mechanical connection. It is basically a flange connection between the two pipe ends. So you have a polyethylene stub end, then you have a steel backing ring, and then it is connected with the bolts around, with the gasket inserted in between.
If the seabed material is rock, then do you need external material for bedding or backfilling?
It depends on the project. So if we are talking about power plant projects, for example, they all require that the pipe is buried. So I suppose that if you have a power plant on a rock bed and it needs to be buried, it would be relatively difficult. If from the pipe perspective, the pipe can stay on the seabed without any issue, you just need to take into consideration that you probably need a heavier ballasting in regards to the wave action and the current action. So pipe can be installed either buried or on the rocky seabed. So it's a normal practice in both cases.
How do you model the ballast submersion and pipe submersion in order to determine the sinking rate and direction of flooding?
So each project is unique. So we need to take a look at the actual seabed and the actual resources on site and the layout of the pipe. And then we can decide, are we going to sink from the onshore or the offshore? In the projects that we have been involved in, we have seen both cases. So sometimes the pipe is sunk from the onshore, sometimes the pipe is sunk from the offshore. It can really be either way.
What was the magnitude of currents while installing in open sea?
I believe that we were in the range of 1 to 2 meters per second in these locations.
But the sinking was done during slack tides, wasn't it? Where you were going to get very low tidal currents.
Possibly, but for Bangladesh, where the tidal range is much more prevalent, it is not installed yet. And in Malaysia, I believe it was just the currents and the tidal range was not an issue there.
Okay. I think we've covered the next question, which was what was the lowering or sinking direction offshore or inshore? And I think we've covered that with our previous question that it can
maybe
be
I can
either...
just point on that, Martin.
Yeah.
In particular case of Malaysia, we were sinking from the onshore.
Okay. How do you dredge for a 1 kilometer length with the dredger when the pipes are in position? If that is not the case, what was the time difference between trench completion or trench excavation and the actual pipe lowering activity?
Well, I'm not the dredging expert, but what I have gathered information from the site is the following. So basically the trench is first dredged fully, and then it is periodically maintained. And it depends on the actual location, the weather, the season, and how fast actually the trench is being filled back by its own, by the nature. So ideally, it would be nice to have a maintenance of the trench a day before the pipe installation. Of course, it depends on the machines that you have used in the dredging and the vessels, etc. But in principle, if you can maintain the trench before the installation, then you would have the perfect seabed ready for submersion.
If you need access manholes, say every 250 meters, do you still tow with the manholes in place, or do you install those separately?
Yeah, that's a good question. So basically, once the pipes are stored in a port or in a safe area, and the pipes have been ballasted, Pipelife has a welder's team which will be sent on site, and this team would drill a hole and would mount a manhole. Pipelife has designed and produced very special and big manholes which are electrofusion welded on site. So our welding team will mount the manholes on site. First, the saddle with the blind plate on top. The pipes can then be sunk with these saddles, which are electrofusion welded on top, to the seabed. Once on the seabed, the divers would go down, remove the temporary blind flange, and mount the risers as needed. So this is the usual process that we do in the depths up to maybe 30 meters.
Okay, for diffuser outlets, do you use inline check valves or duckbill type check valves?
So every project which requires diffusers has a different design. And we have never had one project which is the same as the other. So there are a number of designs. It can be just drilled holes on the pipeline. It can be just an open pipeline in the end. It can be various diffusers under an angles, etc. How these diffusers actually end is usually outside of the Pipelife scope, and it is the scope of the actual designer who is doing the dispersion analysis and the effluent, etc. So they would require duckbill valves or not. In certain projects, we had the duckbill valves, but it was not Pipelife scope of work. So Pipelife has prepared the end of the diffuser so that the duckbill valve could be mounted. So that was more or less what Pipelife provided.
Okay, what is the maximum pipe diameter?
Maximum pipe diameter that Pipelife can produce today is 2.5 meter outside diameter.
Okay, is any testing involved post-installation in the trench or prior to backfilling or post-backfilling?
So any testing of the pipe is under marine contractor's responsibility and what they need to present to their client. So we have been involved in advising the marine contractor how to perform such tests. And it's usually just a leak test at a very low pressure. So we are talking about maybe 0.5 bars or similar, where a certain dye is inserted into the pipe under a relatively low pressure to see if there is any leakage in the joints. So this is the most common testing of the pipelines. If there is a requirement to do a full pressure test, that could be an issue with the ballast blocks because the ballast blocks could crack under a certain pressure because the polyethylene would naturally expand if you're applying full pressure rating for that pipe, which would be maybe 8 bars or 10 bars or whatever.
Right, next one, super duplex or duplex is better for bolts and backing rings? Question.
Yeah, this is a question that we get often on the quality of the steel. So basically, our research has shown that all metals will corrode at a certain point in the seawater. It is just a question of how fast they corrode and what type of corrosion they will have. For duplex and super duplex, they will last a long time. But the problem is if they get a corrosion, they will get this pitch corrosion, which is centered, and it will be more problematic than the overall corrosion of the element. So what Pipelife does is that we use a normal steel and we apply cathodic protection. And in the case of larger materials, such as very large bolts or backing rings, we apply first the hot dip galvanization and then cathodic protection on top. We have seen that this kind of approach is very optimal in respect to the price and in respect to the longevity of the product. I will understand that in some projects, super duplex is preferred if it's, for example, very aggressive environment or it's very difficult to access. Then very high-grade steels could be more preferable.
Okay, backfilling was natural backfill or some rock imported material used for the pipe scour protection? And what was the design life of both pipelines?
So basically, when we talk about backfilling, one of the main advantages of polyethylene is that you can use the excavated material back to backfill the pipe. And by doing so, you are basically temporarily removing the soil which was already there and then taking it back. From the scour protection idea, it is preferable to have the same material back. And if the pipe is sufficiently buried, then no scarring should occur because you would have the natural layout of the seabed again. So you need to take into account that if you are using excavated material, which is of poor quality, that your pipe would not have side supports. So you would need to calculate that and think of that when you're designing the pipeline in relation to the blocks and spacings, etc. If you were to use friction material, then which would be imported, then you can save on the ballast blocks because you don't need the stiffening effect from the ballast blocks because you would get a lot of friction from the replacement material. How is that in relation to scouring, etc.? This is a little bit outside of Pipelife's scope, but usually it's excavated material in our projects.
Yeah, I think as from a designer's perspective, I'd just add to that yeah, typically, unless there's a long-term risk to losing seabed material, you wouldn't put engineered material, but typically you provide that around intake heads and diffusers where there is a bit more of a risk of local scouring.
Thank you, Mark.
Okay. If the pipelines are mechanically connected, I assume by meaning flanged or mechanical couplers between strings, are they still suitable for using HDD techniques?
This is an interesting question. Personally, I would go against it because any kind of such complex connection has its own problems. So if you use mechanical couplers, they are very good at having the internal pressure resistance, but they usually tend to be very bad at sliding. So if you have the grippers gripping on the polyethylene and you have a lot of pulling force, there is a high possibility that the steel grippers would just rip off the polyethylene. So that would be my main concern with this kind of installations and mechanical couplers. If we talk about flange connections, I believe you have a different problem then because you have stub ends and backing rings which are sticking out. So you would need to have a much larger hole, and then you have this at one point just flange connection, which is requiring a much larger bore, which creates other issues. Also, bending of such elements creates another risk that you could overstress the weld, which is between the stiff backing ring and the stub end and the pipe, which is sometimes done, and we have seen such failures in large pipes where you overstress the weld in this transition between the pipe and the rigid zone, which is stub end and backing. So in principle, I would be against using mechanical couplings or flange connections in HDT applications.
Okay, HDPE is getting costlier than GRP due to the increase in oil price.
Right. Okay. So if I can comment on that. So the misconception here is that you're looking at pipe per meter. So if we are looking at long length solid wall pipes, the contractor or the person responsible for evaluating the proposals needs to look at the whole marine installation picture. They need to look at the costs involving how many vessels you need for the GRP, what time they need to be on the sea, how long it takes for them to install 12 meters, connect 12 meters, and then another section, and then compare the whole package, marine installation and the pipe supply with the HDPE solution. And then you will see that the numbers go much more in favor of the HDPE solution because the marine mobilization is much shorter and you can install the pipes much faster. But that requires a little bit different approach that the person who is doing the commercial evaluation understands the big picture, which is the marine installation plus the material supply.
Okay, I think we've probably covered the next 2 or 3 questions, but I'll read them out anyway. Despite long length, some pipe strings still need to be connected. How are those connections made, welding or mechanical? I think we've covered that with the stub flanges and already, so there's nothing else extra to say.
On site, it's usually mechanical connections. If there is a need for welding on site, then it's a different story because it's much more complicated. But so usually long length as much as possible and manageable on site, plus connection on site with the mechanical connection.
Okay, if you're using stainless steel, then is cathodic protection required?
Yes.
Where pipe-to-pipe connections have to be made, have you considered mechanical couplings? Again, I think we've covered that one. Okay, the last 2 questions. So some designs have horseshoe-shaped ballasts. Is it recommended for longer pipe lengths?
What kind of ballast? Can you repeat, Martin, please?
It says horseshoe-shaped. I think it's what we would typically call kennels.
Right. I understand now. So the thing is, the shape of the ballast block is not just from the production perspective, but it is also from what you want to use it for. So if you want to use excavated material, and if you want to use it in weak soils, and if you have potentially a lot of load on the pipe, then your ballast blocks needs to also stiffen the pipe. If you use the horseshoe shaped ballast block, then you're not providing this stiffness and this strength to the pipe. You can only provide it if you have a very tight fit around the pipe. So in principle, in our projects, we always recommend that you have this approach where you completely wrap around the pipes. We have seen other projects where the horseshoe has been applied, and then there can be a couple of issues with those. One of these could be that it just this horseshoe goes down and it just flattens the pipe or ovalizes the pipe too much at that location, or it can easily flip around and have some other issues. So we in principle prefer engineered ballast blocks which provide the stiffening effect around the pipe totally and under control. Also during the installation, you need to have the blocks which provide the stiffness on the pipe, and if you have the horseshoes on at that time, you will not get this support. This is especially relevant if you're having thin wall pipes installed relatively deep. For example, SDR 30 in 25 meters or something, then you need to have an extra assurance on the pipeline. So I would say that in majority of our projects, we do not have horseshoe ballast blocks.
Yeah, I think I can add a little bit to that. Is these horseshoe shaped or kennel types? They're typically used for providing additional weight on top of the concrete ballast blocks, but not sort of as the primary way of causing or providing weight. Because, as you said, there's also this risk that they actually become displaced and move and fall off the pipe during the installation. So yeah, they're usually just used as additional.
Yeah. Correct. Thank you, Martin.
Okay, so the last question we have now is quite a long question, but I think it's all around the same topic, which is around pipe stability. So for on-bottom stability control of HDPE pipes, do you usually use the method presented in the Pipelife catalogue, or do you use standards such as DMV? If so, have you used the methods in DMV, as the forces calculated are quite higher, typically larger than the previous methods? I've tried to abbreviate that question because it's quite long, but I think it's basically saying, you know, what stability standards have you used?
Right. So when we come to stability, and especially stability of HDPE pipelines on the seabed, it is a topic which unfortunately doesn't have a lot of literature, and it doesn't have a lot of standards. Actually, there are no standards referring to the polyethylene installation. So we have two good points here. One is the old Pipelife technical manual, which has been withdrawn in around 2007 or 8 or something like that, because it had some inconsistencies there, and it was not really useful for the very large pipes, which had the need for a more different approach. When we talk about the NVGL recent on bottom stability, there is just one which has recently come out. I haven't read that one, so I cannot comment on that. But the previous one had the issue that it's focused mostly on the steel pipes, small diameters, which are laying on the seabed without ballast blocks. And that actually is much, much different than if you have the pipes on the ballast blocks, because the forces acting on such a pipe are much different. Because if you have the pipe a little bit lifted from the seabed, the waves and motions, etc., will go underneath and over the pipe. As in comparison that if the pipe lies on the bottom or is a little bit submerged in the sand, it will just go over. So the calculations are different and the numbers are different, and the NVGL is more focused on the oil and gas industry and has a little bit higher factors. So what Pipelife does is we expanded on the principle which was presented in Janssen's book from Borealis, where we went into the details of how the polyethylene pipe mounted on the ballast block will behave, and we have expanded on that principle. It is basically Morrison equations, and the Morrison equations we have expanded to include a little bit more precise factors, parameters, and everything else to get to the point where we can design with confidence large HDPE pipelines which are mounted on the ballast blocks.
Yeah, I think as a designer as well, I can add to that yeah, I mean the DNV, it's called DNV F109, is the on bottom stability code from DNV that was introduced, and there's a new version was issued this year in 2021.
Correct.
And yes, it does estimate higher forces because yeah, it doesn't use Morrison's equations, but a lot of the research that forms the basis of that code that has come from the steel pipe and oil and gas industry. But I think also as a designer, you have to look at your approach and liability, and you know, working outside of codes again has issues as well. So it's something as a designer you have to look at and make an assessment on which one is most suitable. But I would say from a designer's perspective, DNV F109 is the guide that is used, and that there are some factors.
I lost you there, Martin. Martin?
We appear to have lost Martin, so I think if you want to close off, because we were just
right. I'll just want to thank Martin for his insight from a specialist design office. Of course, Pipelife is providing just a small bit of the engineering in the whole engineering package that is needed for such a project. So we just provide a specialized HDPE related data and analysis. And it is interesting that, yes, DNVGL is one of the rare standards in the industry. However, it could not possibly be quite applicable for the HDPE because we have a little bit different setup. So I believe it's wise to have an optimum between what are the standards in the industry for some other materials and what can we utilize from the published standards selectively and apply to our own industry until we develop our own standards for installation of HDPE pipelines. But I believe that's a topic for another interesting webinar on that one.
I don't know whether you can hear me again now.
Yes, Martin. Welcome
Okay.
back.
Yeah, sorry, somebody internally rang me, which kicked me out, I think. So yeah, thank you, Ilya, for a great presentation, and we'll look forward to hopefully see some more in the future and some more interesting projects.
I would be happy to. Thank you very much to you, Martin, and to Pipeline Industry Guild, and to all the people who are still with us after an hour and listening to the presentation and the discussion.